Hey, hello, physics students. This lecture is on chapter 7. And in chapter 7, you're really starting to wander into a much bigger world in terms of how you are able to explain the motion of objects. And that's essentially the name of the game right now in our physics course. And, kinematics is a wonderful mathematical description of motion as long as the object is maintaining constant velocity. Newton's laws of motion tell us why an object will change its motion. Right? So we have the first law that it won't change its motion, that it will maintain constant velocity forever unless an outside net force acts on the object. And so now we have a reason why objects will either speed up, slow down, or change their direction. And then knowing how hard they get pushed, we know exactly how that change of velocity is going to take place, is that change of velocity with respect to time. That's the acceleration. And there's nothing wrong with Newton's laws of motion. They tell us why objects are doing what they are doing. Okay. In chapter 7, you start looking at nature in a different way. And I think probably modern day physicists would say that this is the most fundamental approach. That is the lowest level you can get, because you're starting to deal eventually with conservation laws. And we believe that nature keeps track of certain quantities. And one of these quantities will be this idea of energy, which is, a pretty abstract concept. Luckily, we only have a couple types of energies to kind of keep track of in this course. And you wander through your other physics courses, you start adding more ways that energy is going to be stored, maybe in terms of temperatures, electric fields and magnetic fields and so forth. So you really end up with a choice of looking at nature through Newton's laws of motion, or maybe these conservation laws, and there will be 3 eventually before the end of the semester. Neither way is better than any other way. It's not like one way is easy and one way is hard or anything like that at all, but this idea of work and energy and its conservation really relies still on the idea of understanding what the pushes and pulls on an object have to be. So this is why it really kind of comes second after Newton's laws of motion here. So here, I think we're going to probably define this idea of work and then kind of move on from there. And the word work is really used very specifically by physicists. It's not the same word that we use in everyday language. Okay, so if you watch the football team, out on the practice field, they have these big sleds, and a whole bunch of players and coaches jump on the sleds, and the players are pushing and trying to push these things across the lawn, and they're screaming and yelling, and the thing is not moving, but by the end of practice, right, they're sore, they're sweaty, and quote unquote, they've had a workout. But in the strictest terms, at least in physical terms, they may have done no work on that really on that sled that they're trying to move across the lawn. So this word work here, like I said, is it's a very specific definition. And work, it's really a force. So we've been using the letter F for force. We'll kind of keep using that. And I'm going to put a little symbol down here, in a certain direction times a displacement in that direction. Right? So this is really here the force in the X direction. And this X is the displacement in that direction. And it may just seem odd, why define some sort of new character here of force times distance and so forth. And you're gonna have to kind of sit back and have a little faith that by the time we hit chapter 8, we start putting the pieces together, because really there is no reason to really get force times distance unless it has a physical meaning, and it will. It's just going to take a while for us to really kind of see this here. Okay, but this is really, at least a starting point of how we're going to define this idea of work. And so work is force times some sort of distance, and that force is in newtons, and that distance has to be in meters. And a newton times a meter, if they are in the same direction, is going to be defined as a joule. And we're going to use a capital J for that. So those are the units of this thing called work. Okay. Now, using this, it's not really very complicated. And I'm going to show you a couple different, examples here using this definition, and then we'll kind of take it from there. So let's just say, for example, you've got something like this. So you've got an object, and it's just sitting here on the ground here, and you're going to pull here with 100 newtons, and let's say you drag it across the floor 2 meters. Okay, and so you ask yourself this question: okay, did I put a force in the object? Yes. Is the force in a certain direction? The answer is yes. And now, did the object move in that direction? And here the answer is yes. There, in this case, then there's work being done on the object by this force here, right? So the work here is force times the displacement, and my force is 100 newtons. My displacement is 2 meters. And so I did 200 joules of work on the object. Okay, so, right now, you might be saying, well, okay, big deal. And right now there is no big deal, right? And until maybe, I kind of turn the tables here just a little bit and say, for example, let's get that same exact object here. And I'm still going to pull, because, maybe you're only 100 newtons strong. That's as hard as you can pull. And you're still going to drag the thing 2 meters. Okay, and now you ask yourself, okay, is the force in the x direction? And the answer is no, it's kind of in the x direction, but it's not perfectly in the x direction. And which way does the object move? Well, it moves in the x direction. It's getting dragged along the ground here. And so what we need is really the component of the force sideways. And so let's say that this is a 30-degree angle in here. So you're trying to drag this thing across the floor, and you're maybe you got a rope or something tied around it, and it's coming over your shoulder, the rope, and you've got this 30-degree angle here. So 30 degrees, take the cosine and multiply by 100, and my forces, I've got components here, and this is about 87 newtons, and the sine of 30 is 1/2, so this is going to be 50 newtons, if that's a 30-degree angle there. Okay, now take a look here, and try to think this through. That 50 Newton component that is going vertical, that's going upwards, it doesn't make the object move sideways, right? When you lift an object up, it moves the object up if you lift hard enough to overcome the object's weight. So if the thing weighs 1,000 newtons, you better supply at least 1,000 newtons to make the object move. If you can't, then the weight down is going to be the winner of that tug of war. So it's really the 87 newtons here that is making the object move here. So work here is the force in the x direction times the displacement in the x direction. And so it's really the 87 newtons times how far it moved, 2 meters. Right? And that may not be obvious exactly what that answer is. So here I get 174 joules. Okay. Now, take a look-see at those two examples here. It's the same object being pulled by the same force, and the only difference is that the force has changed direction a little tiny bit. Okay, so in one case, 200 joules has been done on the object, and in the other case, only 174 joules. So something is being kept track of here, right? Obviously, one number, the 200, is bigger than the 174. And the reason this is important is that if you were to do exactly this to this object, there's a physical difference in what the object is doing in each case. There's a physical difference. Okay, now what is that physical difference? There's probably many different ways to think about it, but look at that first case, right? All 100 newtons go sideways. Okay, and you look at the second case, the 100 newtons is not really sideways. It's kind of up at some sort of, angle here, this 30-degree angle. So only 87 newtons go sideways. So if you're thinking in terms of Newton's second law, in the first case, you have more force sideways. You're going to have more acceleration sideways. Right? And in the second case, you only have 87 newtons going sideways. You'll have a little lesser acceleration sideways. So in other words, the objects are accelerating differently. If you look at this in terms of velocities, in the first case, after moving 2 meters, since the object has more acceleration, it's moving faster. And in the second case, the object would be moving slower after 2 meters because it has a lesser acceleration. So if you were to go and use Newton's second law and find the acceleration of the object and go to a kinematic, we could find then exactly what those speeds are, right? So there is a physical difference between these two things. And so you can see why having the force go sideways and the displacement go sideways is important. Right? So if the force is at some angle, there's a whole bunch of force that might be lifting up on the object or whatever, but if the object's not moving up and down, that's not really making the object then move faster, at least sideways. And so, what we really want to do here is define work very, very specifically. And so work, it's really, the force in a direction multiplied by the displacement in that direction. Okay. So there is a reason when we take a look here that if the object's moving sideways, we really want the force that's going sideways. And now if we were lifting up on the object, then what would be important would be the component that's lifting up, if the object is actually moving that way. And so there's a physical reason for us to make up this way to multiply a force, which is a vector, times a displacement, which is a vector. So force is a vector, displacement is a vector. But notice that when we have these joules, that it is not a vector. It's really a scalar. So we'll back up just a little tiny bit here. And I think we're going to notice that this is really a vector. That right there is really a vector. That is, they are numbers and their directions. We got to get the directions right. And this joule is not a vector. And so it's just a number. It's a scalar. Okay. And so here is then the physical reason why we're going to create something called the scalar product or the dot product between two vectors, because we have a physical concept now called work that's really going to rely on something exactly like that. Okay, so let's take a look-see here at maybe this thing that we'll call it the dot product of two vectors. So sometimes your math books will call it, and sometimes it's called the scalar product of two vectors. Okay, and so we're going to define a mathematical operation that does exactly what we were just sort of seeing here. Okay, so if I get like vector A, and vector A will have maybe some sort of x components, so I'll call it A in the x direction. Okay, and I'm not sure exactly what the history is, but the x component will have a little I attached to it, and it's a unit vector. Okay, and we're going to have then maybe some y component, and the letter J gets connected to that. And we're going to have some sort of maybe Z component, and the letter K gets connected to that. Now, this would be for a three-dimensional vector. A lot of times when we're dealing with homework problems and so forth, we'll just be dealing with two-dimensional vectors. So let me kind of show you what this notation means. So the math people like this because it really kind of cuts down on the work once you kind of get used to it. Let's say we've got this vector here. I'll just kind of make up something that makes sense to us. Let's say this is 5, and let's say it's a 3, 4, 5 right triangle. And so let's say that this is vector A here. Okay. And so one way to write vector A, now it's only in 2 dimensions, is that we would get vector A here, and the x component is 3. Okay, now I'm assuming here that the vector is in some arbitrary units. Now, eventually, we're going to have newtons and meters and things like that, but right now this is just in some arbitrary units, so I'm not going to worry about that. And then I put this little I right here, and this is called a unit vector. And a unit vector, unit tells you it has size 1. Okay, so if I get 3 times 1, I get 3. But that unit vector has a direction, and that I means it's in the x direction. Why the mathematicians did not use like a little x, I don't know. But the little hat on top of the vector means that it's a vector with size 1. So that's where the unit vector comes from. And then we have a y component in this case that is 4 units in the y direction. And so in this case, vector A can be written as 3i plus 4j. Okay, that is one way of writing it. If I were to go to my calculator and figure out, maybe this angle here with the x-axis, and I were to maybe just use a tangent here. Tangent, that angle is the opposite side, 4 all over 3. And so 4 divided by 3 inverse tangent, that's 53 degrees. So, in our class, up until now, we've been writing this vector this way. We've been saying vector A is 5 units. What are those units are? At 53 degrees above the x-axis, right? So we would write it that way. Now, these 2 methods here are carrying exactly the same information. So 5 units at 53 degrees above the x-axis is exactly the same vector as 3i plus 4j. Okay, so if I were to get 3i plus 4j, those are the components of the vector, right? So these things right here, those are the components. How far sideways, how far up and down. Those components tell us exactly how big the vector is, because you would get x squared plus y squared, 3 squared plus 4 squared. That adds up to 25 is the hypotenuse squared, which is exactly 5 units long. So even though we don't see the size of the vector directly, we can get it. And with 3i plus 4j, we don't see the direction given to us directly, but we can get it. Okay, so we would just draw a triangle with 3 sideways, head to tail, 4 going up. Go from where you started, get your resultant vector, and we'd be able to write it that way. Okay, so now, so this is kind of, a new way of writing vectors for some of you. Some of you have been introduced to this already in your math classes. Now, taking a look at what we have above. So just kind of, recall this here. So let's just kind of go up here to this idea of work. It's force in a certain direction times the displacement in that direction. Okay, so what we want to make up is a mathematical operation that does exactly that. Okay, so and so when I take a look at this example here in blue, 100 newtons was at a little bit of an angle, but some of that force, some of the force which is going sideways, the x component of that force times the displacement in that direction is really what we wanted, right? See, the x component times the x displacement. That's what we're trying to define. That's what this thing called the dot product or the scalar product is really going to do here. Okay, so if we get two vectors, and so let's define this in here. We're going to define one vector dotted into another vector. And so this is called the dot product. So it really is a big dot. And then, sometimes people call it a scalar product because it's two vectors multiplied by each other, but you get a vector out. Okay. What you're going to do here is get the x component of vector A times the x component of vector B. Isn't that what we just did above? We had force going this way, 100 newtons, but 87 was sideways. And then we multiplied it by the component going sideways, which was 2 newtons. That's exactly what we have written down right here. Okay, that's exactly what we want. But, there may be more components that are in the same direction. And, we could take this out really, as many directions as we really want when we start doing linear algebra and so forth here. But we'll write it that way. So this is the definition of what that dot product is. You just get the components that are in the same direction and multiply them and add them all up. And that's all you really kind of have to do here. Now, there's going to be more to this operation here in a moment, but I think it's just enough for us to kind of get started here with this. So for example, let's say we've got this. Let me put a little EX here for an example. Let's get a vector like this. Okay. And maybe let's use exactly that same example we just had. Let's say this was 100 newtons, and this is at 30 degrees. So this is a force vector in this case, right? So this is my force. Okay, so how do I write the force in this notation? Well, what you have to do is find the components. And so you're going to use sines and cosines for that. So the sine of 30 is 1/2. And I think we already found that this was 87 newtons. So I didn't do anything magical there. I just remember the number from a few moments ago. So my force can be written this way. 87 newtons. Now I have units in the x direction. It's funny, we put an I for the x direction, but that's just the traditional way of doing this here. Plus 50 newtons in the j direction. So that kind of looks odd. And then what we had was the object actually moved this way, right? 2 meters. And that's the displacement vector. That's the displacement vector. And so my displacement vector is 2 meters in the x direction. And it doesn't have any y component, but it doesn't matter if you write that down or not. You could write 0 meters in the j direction, which is really the y direction here. And that's a vector right there. So here's a vector. And so what we can do here is use this idea of this new operation. That work is F dot the displacement. Okay. And so what that really means is get the x component of the force right there. You get that x component, and I'm going to multiply it by the x component of the displacement. So I'm just going to multiply those two. So I'm going to get 87 newtons. I'm going to multiply that by 2 meters plus, 50 newtons. And the 50 newtons is in, right, the j, or the y direction, and I'm going to multiply it by exactly what I see here in the displacement vector, 0 meters. And I'm going to add those up. So here we're only living in 2 dimensions, but 2 times 87, and this comes out to, I guess that was at 174 newtons, I hope. That's what I kind of remember here, because 50 times 0 is 0. And that's, how we're going to, multiply these vectors. So, we want to have a physical context here, but, there doesn't need to be. That is right. The math people are going to play with this stuff and look at it for its interesting aspects, all together here. So this actually, goes pretty fast once you kind of catch on. So for example, if we just, kind of made up, some vectors here. Let's say we have 2i minus 3j plus 4k. That's one vector. Maybe vector b is something like 1i plus 2j minus 3k. When you dot them, when you go a dot b, all it means is that you get the x components and you multiply them. 2 times 1, right? Just the x components, or what's connected to I. So get those, multiply them, plus the y components. So one is -3, the other one is 2, plus add them all up, the last components, and that's it. And we just add them all up. Okay. So, in this case, I guess we have a 2 plus -6 plus -12. And so this adds up to what, 18 with the minus sign plus 2. So maybe -16. And there might be some units here if these things have got some units other than something that's arbitrary and so forth. Okay. So it's actually, very meaningful in terms of work, that it's the force times the displacement in the same direction. And so we just made up a new way of multiplying vectors that does just exactly that. We get the first vector, the force vector in this case, times the displacement only in that direction. So you're just multiplying components together here. Okay. Now, if you play around with this long enough, you find that there are some interesting aspects that happen to be true that may not be obvious to you, right up front. So let's take a look at this scalar or dot product. If we do a dot b, just a couple of generic vectors, that is a in the x direction times b in the x direction plus a in the y direction times b in the y direction plus a in maybe the z direction and b in the z direction. And so that's what we've been doing so far, and that works. But it's kind of interesting that what's also true is that when you do this, it's equal to something else, and it's equal to the size of vector A. So there's the notation in your textbook, right? Absolute values around a vector means the size of the vector, the magnitude, times the size of vector B times the cosine of the angle between them. And this really probably should not be a terrible surprise to you, because if you back to our original example with the 100 kind of going out of sight, what I really did is get the cosine of 30 to find out how much of that 100 went sideways, which turned out to be 87 newtons, right? So I needed the cosine to grab this vector that's not sideways, so I can multiply it by how far it's moving sideways. So I needed the cosine, and that cosine is the angle between the two vectors. So the 100 newtons was like this, the displacement was like that, and this is the angle right here. This is the angle between A and B. So let me, I wonder if, I can kind of convince you that it works this way here. So let's just kind of get something here, kind of straightforward that we can picture. When these things start getting in 3 dimensions and so forth, they're very difficult to start picturing. I know some people can do that, but most of us can't. So let's just say that we've got, maybe this vector right here, for example. Let's say vector A, and we'll go back to something kind of straightforward. It's just 5i, so it's in the I or the X direction. So vector A just goes sideways, and so it kind of looks like this. So there's vector A, and it has size 5 and has a certain direction. And then we're going to have vector B, and let's have vector B be something like this. 3i plus 4j. And maybe what I should do here is put B in color. So B goes out 3 units, and then it goes up 4 units. So 3, there's 4. So vector B looks like that. All right. Now, a 3, 4. So vector B has size 5. Do I know that angle right in there? Well, I probably can figure this out here, but let's just kind of see how this plays out. If I were to do this operation, if I did A dot B, it's 5 times 3, and since A has no other components, everything else is just 0. So it gives me a value, a scalar, a number of 15. Okay, and now I'm going to actually go to my calculator and make sure that I understand exactly what this angle is between vector A and vector B, because this right here is angle theta, and so 4 divided by 3 inverse tangent, so that's 53 degrees here. Okay, and so let me see if this happens to be true, because what's supposed to be true is that A dot B equals the size of A times the size of B times the cosine of the angle between them. But A dot B here turned out to be 15 units. The size of A here is just 5. What's the size of B? Well, that's the size of the full-blown B vector, and it's 3 squared plus 4 squared, and so it's also 5 units. Okay, but there's a 53-degree angle between the two. So vector B is here green, and in the little picture, and vector A is 5, and so we have an angle in between here of 53 degrees. And so it just happened to be true. If I get 53 and I take the cosine and I times it by 25, this turns out to be true, that is equal to that. So it really does work that way. And so this is going to be important, in your math classes for something called directional cosines and so forth, and it'll be part of your vector analysis course and so forth. For us right now, though, we want to do something that's kind of physical with this, with forces and displacements. Eventually, as you go through your physics courses, we're going to have other reasons to be using a dot product. So you'll see other physical quantities that will be defined exactly the same way here. Okay, so let's take a look here. So, I don't think you have this in your package stuff, so you're just going to have to maybe take some notes here. But I've got a force that's 2i plus 4j minus k. So there's really a -1 kind of hiding there in newtons, which moves an object whose displacement is given by vector d. So my vectors here are in bold print. And so that's 3i plus 4j, and that's in meters. Okay, so newtons dotted into meters will be this new unit called a joule. Right now, I don't have a really good feel of what a joule is, but as I start getting more and more experience, and as you get more experience, you'll start having a better feeling for this here too. Okay, so let's take a look here what we need to do here. Find the work done on the object. Okay, so for this, I'm going to use just the definition that work is F dot the displacement. Okay, and what that really means is I multiply X components by X components. So in the F vector, the force vector, the X component is 2. And in the other vector, the X component is 3. And I'm going to add them all up. Then I'm going to have 4, the Y components times each other times 4, plus minus 1 from this component there, times the K component in the vector D, and there isn't any. So it really is 0 here. Okay, so that 0 will knock out that minus 1 here pretty fast. And so it looks like I've got 6, 2 times 3 plus 4 times 4, which is 16. So what is that? I think that's 22 here. And our units are newtons dotted into meters. So this is 22 joules. Okay, once again, I don't know if I have a great feel for joules, but it is what it is here. Okay, so that's the work done on the object. Okay, the more work I do on the object, that means there's more force going in the direction that it's moving, so it means that it's picking up at a bigger speed. So right now, that's kind of the physical meaning here that we kind of really want to have here. Okay, find the magnitude of vector F. This might be kind of new for some of you. Depends on how far you've gotten in your calculus course and so forth. But if you have a vector in 2 dimensions, its size is just one component squared plus the other component squared. It's sort of like D, right? So vector D, it's 3 plus 4. So I've already kind of used that, a few times here. So 3, put them head to tail, 4, and there is vector D. So the object is moving that way. So what is the size of that vector? So we write it this way, right? D squared equals A squared plus B squared. So 3 squared is 9, 4 squared is 16. And so the size of this vector is 25. And then we take a square root, and the size of that vector is 5. Now, if you have a vector like F here that has an X component, a Y component, and a Z component, you do exactly the same thing. It's a little harder to draw, but the operation is exactly the same. So the size of that vector is going to be the X component, which is 2, and it gets squared. So just like the Pythagorean theorem, but we're kind of like doing the Pythagorean theorem, kind of like in 3 dimensions here, right? So you get the X component, right? And then you get the Y component. And so I'm going to get the Y component of vector F, and that's 4, and I'm going to square it. And I'm going to get the Z component, which is minus 1, and I'm going to square it. And that's the size of the vector squared. So it's kind of like the Pythagorean theorem in 3 dimensions here. So A squared plus B squared plus the other component squared. Add them all up, take a square root eventually when you're done. So 2 squared is 4. You got 16, and 1 squared here, I guess it's just 1, right? So that's the size of the vector squared. So I think that's 21. So the size of this vector is the square root of 21. And so, that's some number, I guess maybe between 4 and 5 on your calculator or something like that. Okay, so, I probably kind of see why, this is being asked of us, but this is kind of typical type stuff here. Find the angle between F and D. Okay, so what's supposed to be true is that F dotted into D is equal to the size of F times the size of D times the cosine of the angle between them. Now, F dot D, I already did that up above here, and that was 22 joules. So this right here is 22 joules. The size of F is the square root of 21. The size of D is 5 times the cosine of the angle between them. And here I've got a 3-dimensional vector, I've got a 2-dimensional vector. I'm not very good at really trying to picture these things, but I do have some mathematics that can spit out that answer pretty quickly here. So when all is said and done, I'm going to get 22. I'm going to divide it by the square root of 21 times 5. And I'm going to take the inverse cosine of both sides there. So I'm going to try this. 22 divided by 21 divided by 5, inverse cosine. And so I get something about like 16.2 degrees here, I think. So as long as I didn't mess it up on the calculator, maybe I'll try that one more time. Divided by 5, 21 square root equals, take it inverse cosine. I kind of get the same thing both times. Okay, so if you have not seen the dot product before, this is something that is a definition. It's a definition of a new mathematical operation. And it's got some interesting things here. It's not very hard to use, but like anything new, it's going to take you a little bit of practice and stuff. So you want to memorize the definition of work, right? It's force dotted into the displacement. And the dot product now means it's the force component times the displacement component that are in the same direction. So we're getting x's from the force vector multiplying by x's in the displacement. Forces in the y direction times the displacement in the y direction. Forces in the z direction times the displacement in the z direction. We add them all up. Okay. So if you're not pushing in the y direction, and if the object moves in the y direction, that force didn't make it move in the y direction. It was already doing that. Right? It's the force is what's going to be changing the velocities and so forth. So it's important to remember exactly what's taking place here, because all the physics you've learned so far, it's all true. Nothing has changed. We're just trying to add some sort of nice mathematical operations here, so we have a compact way of being able to write these things out that have some sort of physical meaning. This might not be a bad place to take a little bit of a break and maybe try to tackle a couple of the problems that you see in your homework and in the book with dot products and so forth. And I'm going to kind of keep going here in chapter 7 and just kind of keep working through the different ideas, because it's really going to be some of this new terminology and these new mathematical operations really are going to be put into practice really in chapter 8. So chapter 7 and chapter 8 are really connected at the hip, and one is really kind of the preliminary information. So a good place to take a break if you need to, but I'll just kind of keep going on and see exactly what we need to do here. Okay, so kind of chapter 7 here, kind of like part 2, work done by a non-constant force. So far, I've been talking about a force that was constant in nature. And so let me kind of think about this here. Right? Work is F dot the displacement. And so let's just say I have a constant force. So this was kind of in the back of your mind here. Let's say that we've got a constant force. Okay, and let's say that that constant force is in newtons, and let's say it's like 5 newtons, and I supply 5 newtons, and the object moves, and it moves in the x direction, so this will be in meters, and let's say that it moves 2 meters, okay? And so you go, oh, this is pretty easy. So you supply 5 newtons of force in the x direction, it moved 2 meters in the x direction, so it's just 5 times 2, right? So my work here is 5 newtons times 2 meters, as long as they're in the same direction, and I get something like 10 joules. Now, when I take a look at this little diagram that I've got, 5 newtons is really this right here, right? I went up on the y-axis 5. 2 meters is really how far I went this way. And so if I really get that 5 times that 2, what I really have here is the area, right? The area is length times width here. And so the area here equals 5 newtons. That's the height of the triangle times the kind of the length of the triangle, 2 meters, and I get 10 joules. So it's not really a coincidence here that work equals the area under the curve. When I say the curve, in this case it was straight line, and that's of the F versus displacement graph. So that will be something that will be true all the time. If we have force here and we have displacement here, whatever area we've got underneath is going to be our work done. So if I get something that is not constant in terms of force, so if you have something, say, we'll say number 2, a non-constant force here, so that might start looking, something more like this here. So let's say we've got force here, newtons, and maybe our displacement down here. And, the force is doing something like this. All right. So the force is not a single number where it just tracks perfectly sideways on the graph. So it got big and it was changing and so forth. What you would do, like in a math class, is that you'd kind of come in here and you say, well, if I get in here really tightly and I could just about draw like a little tiny straight line up there, even though I've got some sort of maybe polynomial function or something here that's kind of curving, but I would probably get like this force that I would call maybe force 1, and I have like this little delta x1 right here, and I could say that my work is sort of like that force 1 times my delta x1 plus, right, and then I kind of come next to it. And, maybe I have a force 2, maybe I have a delta x2, plus force 2 times delta x2. And I keep doing this until I have the full area underneath that curve, right? So you got to kind of fill it all in here to get all of the areas. So you're going to have all of these little tiny rectangles in here, which are just height times the width. And so you just kind of keep adding these things up, and you just add them up, and you just add them up, and you just add them up. And when you add them up, that really means a sum, right? So this is why Newton's going to use something like the integral sum, big S here. And what you do is you make your rectangles really, really skinny, right? The skinnier you get, the better off you are in terms of, losing any sort of approximation. And so you pass through that limit, right? And so, the work is, the sum of all of these forces times these delta x's. And so you add them all up, but eventually, your work is going to become, when you pass through the limit, right? When you take the limit here as delta x goes to 0 of this function here of getting one of these things multiplied by the other, and that becomes another sigma sign, right? A big S of F dot into the displacement, right? In this case, I'd have like a dx or something like that. And so we know that, and a different color would be good here, that this means that the work in general is the area under the curve of that operation, right? Force times displacement here. So now let's take a look here, and I'll try to put that into some sort of usage here. Let's say that we've got something that we can do kind of two ways here. And so maybe we've got our force here in newtons, and maybe our displacement here in meters, in the x direction. And let's say that the force does something like this. And this is out at 1 meter, and maybe this over here is at that spot right there is at 1 Newton or something like that. Okay, and so the function is doing something like that, and then maybe it does something like that. It comes way out here, and maybe the spot on the x-axis is here is like 4 meters or something like that. Okay, so And you're asked this question right here, like how much work is done on the object from x equals 0 to x equals 1 meter. Okay, so you've got a couple of choices here to try to tackle this. You could say, well, it's an area, okay? And so it's the area under, this curve right in here. And so that's just the area of a triangle. And so it's the area of a triangle, which is a 1/2 base times height. And so it's 1/2, and that base is 1 meter. The height is 1 Newton. 1 times 1 is 1, cut in half. The area equals the work. So 1 times 1 times 1/2, I have 1/2 of a joule here. Okay. Now, if you say no, we have a little more sophisticated way of being able to handle this, and what I can do is say that my work is F dot dx, and dx is going from 0 to 1, and you would have to know here, because force is a vector and displacement is a vector, you'd have to know what that force looks like in terms of its function. And it goes over one, up one. This is just the line here, I think this is just the line. Y equals mx plus b. The slope is 1 times x, and the intercept is 0, so y equals x here. So I think my force here is just x and then times dx. And so when you integrate that, I guess what the power goes up by 1, you divide by new power, then you evaluate at the limits here. And so you end up with 1/2, and with arguments here, that's going to be joules as well. So if you do this, with calculus, you should get exactly the same answer if you're able to use geometry. Now, if you have something that's actually curving, right, you're going to have a very difficult time, doing anything other than some sort of Riemann sum or something like that to get an approximation of that area and so forth here. Okay. Now, how much work is done from maybe 0 to 4? Well, from 1 to 4, it's just this area here, and that's the area of a rectangle, right? So this area here would be, that goes up to 4, so the base would be 3 meters long, and the height is 1 Newton, and so that is 3 joules. And so I guess my total work here would be that 3 joules plus the triangle, 1/2 joule. So I'd have 3.5 joules of work done by this non-constant force. Between 0 and 1 meter, the force is changing. And between 1 meter and 4 meters, it's not. So I have a little bit of an easy situation where I have a constant force, and then the situation from 0 to 1 where it's not. Right? You have to deal with that a little tiny bit differently here. Okay. So, how useful is it to consider, forces that are not constant? I think most forces probably really, aren't that constant here. And it's traditional, and your textbook does this very nicely. He's going to introduce now a physical system that is literally everywhere. And is a non-constant force, and people just use this all the time, and that's a spring, right? So it's any sort of mechanical clocks, they're in your cars, they're opening your garage doors, right? They're on your couches and your beds, the springs there. Your car doors open and close. If you've got doors that automatically close and so forth, you might have some sort of spring mechanism there that's doing that. So I mean, they're just really kind of everywhere. And there really is two types of springs. There's a compression spring where you push it together and then it wants to kind of come back. Then there's an extension spring where you pull it and then it kind of wants to sling back. So we have two kinds of springs, but the good news is that we don't really have to treat them differently at all. In fact, we don't have to distinguish between them whatsoever. That's kind of the good news here. Okay, and so there's actually an interesting story. It used to be a best-selling book, maybe like 20 years ago or so. I think it was called Longitude. And the King of England, centuries ago, was given a huge prize to anybody that can tell his navy how to figure out the longitude on planet Earth. Latitude is pretty easy. You can just do that in 10 seconds if you have a clear view of the night sky. And so all you have to do is get they call it a sextant, but essentially it's just a protractor to get the angle up to Polaris, the North Star, and that's your latitude. So voyagers could figure that out very easily. Now, longitude is a very difficult situation. Essentially, what you need is a good clock to do this. And imagine having some sort of little hourglass clock with sand that falls on a ship that's kind of rocking and rolling on the ocean. You can kind of see that that's not the best method. 400 years ago, Galileo kind of figures out that a pendulum swinging is a good timing device. And once again, you get that kind of device and you put it on a ship that's in motion, and it's going to have troubles too. People started, and it was not easy. And eventually, it was a family that worked on some sort of clock mechanisms, right? A whole bunch of screws together and gears that were working together, and cogs that were all being pushed by, right, turning some sort of knob that is compressing a spring that then starts pushing something over a long period of time, and it keeps the clock mechanism working at a constant rate. And eventually, if you know how fast you're going, and then you have a good time, then you know exactly how far you are sideways, east and west, which is your longitude coordinates, from someplace in England. And so spring suddenly became kind of important. And Newton's going to have a contemporary named Hooke. And Hooke will have his name attached to springs. And so he's going to do some research here and find out that springs, for the most part, behave in a very nice way, but it's not a constant way. Okay? So if you have a kind of a spring here, and if it has no stretch, it's not really supplying any force in it. But the minute you stretch it and you attach something to it, if it's an extension spring, it's going to want to kind of pull back, and it's going to want to pull this object. And what you find out is that the further you pull it apart, the bigger the force is, because that elastic material then is really trying to get back to, kind of where it was. So a spring is a very common dynamical system where the force varies with how far you have stretched the spring. And that's exactly what Hooke's law actually says here. And so Hooke's law says that the force is a vector, that a spring exerts on an object is proportional to how far you have displaced it. Okay. And so X is kind of our displacement since, our notation since chapter 2. And displacement is a vector. So the more you displace it, the more force. And when you say proportional, it means that it works nicely. That if you double the distance you have pulled the spring apart, then the force on the object is going to be twice. Or another way of looking at it, it takes twice as much force on your part to actually get that spring and pull it apart twice as far as it was before. If you want to get it and pull it even further apart, you want to pull it 3 times further apart than you had before, it's going to take 3 times as many newtons to do that. Now, proportions are good, and those are nice straight lines on graphs, but you're off by a constant of proportionality. And the constant you're off by, if you give this some thought, depends on really what kind of spring you've got, right? If you get something like a little slinky, I mean, you could just give those things a dirty look and they start wiggling all over the place because, they're very kind of loosey-goosey. Now you get something that's like a spring that's in your garage door. If you have an automatic garage door opener, you probably can't grab those things with your hands and really compress them hardly any at all. Right, it's probably beyond most humans to be able to do that. But you can hop on the fender of a car and you can see it compress just a little tiny bit, right? Because you've got some springs in there that are helping with the suspension of the whole system and so forth. And if you got two guys and then hop up on the fender, you're going to compress that spring twice as much if each person is the same weight and so forth. So this is Hooke's law. And it says that the force of a spring is proportional to its displacement, but you're off by a constant of proportionality. And that constant in all textbooks is given the letter K. And that K is called the spring constant. And the spring constant is really a number that gets attached to every spring. So when you buy a spring, it may tell you what K is. And if it doesn't, it's very easy to measure. You just put a force on the spring, you see how far it stretches, and that's that. Okay, now let's give this some thought. Let's say you've got a spring here. And let me just maybe kind of draw a spring. So let's say that the spring is like that, okay, and you attach it to a wall. And then what you do is that you stretch it out, right? So you stretch out the spring, and the spring is displaced this way, right? We displaced it to the right. Now, if you're hanging on to the end of the spring, which way is the spring pulling on you? And the spring would be pulling on you this way, right? The force of the spring is that way. The spring wants to spring back. It wants to go back to where it was. So the displacement's one way, the force is the other way, and springs work that way. So there's a minus sign here. And that's because F and X are in opposite directions. And that's just the way the springs work. For the most part, it's not a big deal. A lot of times people just even forget that there's a minus sign there because it doesn't have a lot of operational effectiveness other than to be complete and tell you that, okay, there's a force that the spring exerts, you displace it, and that force and displacement are always in different directions and so forth. This K is called the spring constant. Okay, and then for us, the spring constant doesn't have the minus sign. The minus sign is there for the vectors. The K will never have a minus sign. It's just a positive number that defines how difficult it is to stretch the spring. And a lot of times people will call that the stiffness of the spring, right? A slinky, right? They just flop all over the place, maybe something that's like in your car would have a bigger K because it takes a couple of guys to jump on the fender just to get it to maybe squish, maybe like a half inch or a quarter inch or something like that. And if I take a look at Hooke's law, K is going to be force divided by distance. So K is in newtons per meter. And the force and the displacement are in different directions. So one of them is positive, one's negative, and there's already a minus sign there. So those two minus signs cancel out. And so K is in newtons per meter. In America, newtons might be pounds and meters might be feet, right? It's going to be force per distance, but it's called the spring constant. And that number is good for the spring as long as you do not go beyond the elastic limits of the spring. So you can straighten out a spring and then you ruin it. And then it no longer has the same elastic capabilities. And so you can break a spring. Now, Hooke's law is not just good for springs, but it's really good for anything elastic. So something like rubber bands or bungee cords or anything like that at all will behave much like a spring does. And it'll be exactly the same mathematics. So don't get too worked up about seeing the word spring connected to something that looks like a rubber band in a homework problem, because they are elastic materials. So, these elastic materials or springs are really being brought up here for really two reasons. One is it's a non-constant force, because take a look at the force law here. So the force law here is non-constant. The force varies with how far you stretch the spring, right? So it's just not force equals a number. The number changes depending on what X happens to be. K will not be changing for the spring. So this is a good example of a non-constant force. It also happens to be a very useful device that is just kind of everywhere. There are just so many springs all over the place that we kind of don't even notice them for the most part. But also, eventually, the most complicated motion you will look at in physics 101, 102, 103 is something that bounces back and forth. That's exactly what springs do. So if you kind of introduce it now, you've got a little bit of feeling for K's, the spring constant, and how they work and so forth. When you start getting into this more complicated, harmonic motion of something bouncing back and forth here. The other reason that you bring it up right now is that if you get a spring and it's an extension spring, you pull it apart, when you let go, it moves. So if I do work on it, right, I displace it that way, pull this way, it displaces this way, my force is that way, I let go, it can make something move, right? So in other words, springs will store energy. And that is important. And people have been using this for maybe, 3,000 or 4,000 years. When you think about something like a bow and arrow, right? You get a piece of wood, maybe a piece of leather, and when you pull, right, the elasticity is storing energy, and then it can make something move. And eventually we'll call that motion kinetic energy. There's a couple things here for us to kind of really pay attention to. One is Hooke's law, okay? And the other is that elastic materials can store energy. And energy is this idea of joules. So work is a generic term for this thing called energy. And elastic materials can really store this. Okay, so I think that we can probably demonstrate this here, that the work of elastic materials of a spring, right, is going to be, you start, someplace, you end up someplace, and that's the force of the spring times the displacement of the spring. Okay, and so if I pull a spring to the side, and if my force is minus kx, so if it displaces to the right, then my displacement has to be negative, and it's going to go back to 0. And then I've got a dx here. And so, work is F dotted into the displacement. So there's the force of a spring. Hooke's law, here's the displacement, and we've got our little dot product in there. And when I start figuring out how much work it takes to stretch a spring, K is a constant, and it comes out really here for free. So that really matters not. There's this minus sign that flips around. The power goes up by 1, divide by the new power, and I'm going from minus x out to 0. And so when I start evaluating, right, I get 0 minus, and then minus k x squared all over 2. And so the work that it takes to stretch a spring is 1/2 kx squared. So there's a couple of things to realize here. We'll get to the second part, which is really going to be the important part here, really kind of in chapter 8. This is the work to stretch a spring from 0 to x. Okay, that's chapter 7 thinking. That's the work to stretch the spring from 0 to x. And you know, it's probably fair game for you to say, okay, so what? The so what is really you know, the second part here. This is also then what we're going to say is the energy stored in the elastic material. The work that you do on something like a spring is going to be the same as the energy stored in the material, and that's going to be critical, because what we're going to find out is that nature keeps track of some quantities. We don't know why, but it just does. One of these quantities is joules. It keeps track of joules. And so an elastic material, if you stretch it, the amount of joules that you put into stretching it is now stored in that material, and you can get it back, right? It can make the arrow fly. So you can pull the bow, put a force on it, and then it comes back in terms of motion, because now you can do work on an object. You can supply a force and make it move. And that's going to be really, really kind of key for us here. Okay. So really kind of what's in this box right here is something you're going to memorize. You're going to memorize that work of an elastic material, usually called a spring in your book, is 1/2 kx squared. And you should kind of know exactly where that came from, right? So you should be able to do that little derivation stuff there. Okay, so for chapter 7, it really ends up with this idea of something called the work energy principle. And this is where now the rubber is starting to meet the road, that the net work done on an object, you supply a force and it moves, is equal to the change of the object's kinetic energy. And so there's this new term showing up right here, and we need to know exactly what that means, and then see exactly, you know, how we sort of handle and think about this. Okay, so an object's kinetic energy we'll have 2 types of kinetic energy this semester, but translational kinetic energy, KE, and we'll put trans right here for translational, is defined as 1/2 the object's mass times the velocity squared. You go, well, where does that come from? Well, right now, it's a definition because there's a game being played and we haven't quite got to the game yet. So you're still learning about, oh, there's pawns and there's bishops and there's knights and there's rooks, and they have these different names and they can move in certain ways, but you're not seeing the game being played yet. That really is kind of held off until chapter 8. So this is some sort of the preliminary materials. Now that 1/2 is just there for us to get the right answer in terms of the accounting of the number of joules. But take a look here at the units here. 1/2 carries no units, but mass is in kilograms and velocity is in meters per second, and that gets squared. And so what you have here is kilograms times meters all over second squared here, right? And let me kind of rewrite this here as kilograms times meters all over second squared times meters. That right there is mass. That right there is acceleration, meters per second per second. Mass times acceleration, that's a Newton dotted into a meter. This is a joule, right? So the units here of m times v squared come out in joules, just like all the other work really should be. Um, and using this is not very difficult. So let's say that right, you get a baseball, and let's say that the mass here is 600 grams, and you throw this thing here at 20 meters per second. When you do that, it takes work to do that. You have to supply a force over a distance. So for a pitcher, right, the force probably starts somewhere back behind their head, and then it ends up, about the length of their arm away. So they're probably pushing the ball for about a meter or so. And so they put a force on it for about a meter, and they do work on it. And that work then makes the object have this translational kinetic energy, which is how fast it flies across the ground. And, to find out how much kinetic energy this object has, we get 1/2, we get its mass, and we get its speed, and it's 1/2 mv squared. And so we run to a calculator and we try that. 20 squared is 400 times 1/2 times 0.6. And I think I'm getting on my calculator 120 joules here. So let me try that again. So 0.5 times 0.6 times 400. And I get 120 joules. Okay. And so the pitcher of this ball that threw this ball, it took at least 120 joules to move the ball. Okay, so there's going to be a little bit of friction in the joints and in the bones, and and that sort of thing. But this is the energy that you gave the ball. It took at least that amount to get it going this fast. Probably more, right? And so the pitcher gets tired. Right? The arm gets tired, the body gets fatigued because you're using energy for pitch after pitch after pitch, and so forth here. But this works for baseballs, this works for roller coasters, or really anything, right? This will work for an electron moving through a TV tube. This is exactly how we find its translational kinetic energy. And so this translational kinetic energy, this will be very important. This is something you memorize. 1/2 mv squared. You memorize the units, right? Mass has to be kilograms. Velocity has to be meters per second. You square that, then it comes out in joules like it should, right? This is something that we will memorize because we're going to be using this over and over and over again here. Okay, so now let's take a look at an example here. So I'll give you a second here. Maybe hit pause and copy this down. This says an object of mass 5 kilograms is resting on a frictionless tabletop and is pulled to the right by a 20 Newton force directed along the horizontal. What's the final speed of the object? Okay, so to do that, we use this idea up here of the work energy principle, that the net work done on the object is equal to the change in the object's kinetic energy. Okay, so I'm doing work on the object and I'm going to change its kinetic energy. And that's how, right, I'm going to try to sort of tackle this thing here. So what we've got going here, it's an object, okay? And it's 5 kilograms, and it's resting on a frictionless tabletop, and it's pulled to the right by a 20 Newton force directed along the horizontal. Okay, what is the final speed of the object? Let's say that, I think what we need here is, probably like how far the object moves. So let's just kind of say that this object is going to move here. Let's say it moves 2 meters. Okay. And so this principle, right, the work energy principle, some books call it a theorem, says that the work that you do is equal to the change in kinetic energy of the object. So you're pushing the object, right? When you push an object, you change its motion, you accelerate it. if you figure out the acceleration, you can use kinematics if the acceleration is constant. That's not always the case. Like a spring, the force is not constant, the acceleration is not constant. So now you can't use kinematics here. So you're left to having to use other means here. And so this is why this is going to be an important aspect here. How much work did I do here? Well, work is force in the x direction times the displacement in the x direction, and a change of kinetic energy is my final kinetic energy minus my initial, right? That's how I always find a change. Get what I have now, final, subtract off what I had before. And I am supplying 20 newtons of force for 2 meters. And the problem says it started from rest here, did it not? An object is resting, it's resting. So it's resting. That means it starts from an initial speed of 0. And what's floating around the back of your head is that kinetic energy is a 1/2 mv squared. There we go. So that's what's floating in the back of your head. So if it starts from rest, then the initial velocity was 0 meters per second. So my final kinetic energy is 1/2 mv squared. That's my final. It's my final speed. And this one right here is 0. So this allows us to be able to say 2 times 20 is 40. And that's joules equals 1/2. I forgot the object's mass, or it is 5 kilograms. And I should be able to find the object's speed this way. In other words, the work that I did here is going to change the object's motion, and it goes into this thing called its kinetic energy, right? And so the kinetic energy is a number, if you keep pushing, keeps growing. And so it's kind of an instantaneous type speed here. So this is at the instant where it's traveled like the 2 meters or something like that. So 40 times 2 is 80. So we have 80 here, 80 joules. Divide both sides by 5 kilograms equals V final squared. And let me try this on the calculator. 80 divided by 5. And then I have to take a square root, and I think I come up with 4 meters per second here. So 80 divided by 5. So this is 16. And if I really watch my units here, they really should work out correctly. So joule is a Newton, right, times meters. And a Newton is mass times acceleration. And there's a Newton right there. Times distance, all over 5. That's all over kilograms. I already did the division. So kilograms will cancel out, and I have meters squared over seconds squared equals a final velocity squared. And so this is going to imply that my final velocity here is 4 meters per second. 4 meters per second. Okay. So this thing is called the work energy theorem, sometimes the work kinetic energy theorem, but the work that you do can change an object's speed, and that speed is locked up in this thing called kinetic energy. Okay, now what happens, maybe you got something else here. An object of 5 kilograms, same object, is resting on a rough tabletop. Oh, so it's not frictionless, and is pulled to the right by 20 Newton force directed along the horizontal. The coefficient of kinetic friction is 0.3. What is the final speed of the object? Okay, so exactly the same problem, except now that we've got some roughness here. Okay, so I've got some roughness. Okay, so here's the object, and I'm going to pull it to the right with 20 newtons. And so I'm going to have something like friction going the other way here, right? So we've got the force of friction. And that force of friction, typically you don't get that for free. You got to work for that a little bit. So we're not really done with all of our forces here. We've got weight going down, and you've got a normal force going up. I think I'm going to just take a minute and just take a look at these forces here. So I'm going to add up all my forces in the y direction, so equal to mass times acceleration. And I'll call up positive and down negative. And as I drag this thing across the floor, it's not going to even move up and down. So I've got the normal force going up. I've got weight coming down. It doesn't accelerate that way. So in this case, the normal force is the same as the object's weight. That's not always true. And so I don't ever want to make that assumption that that happens to be true, because that's only true really sometimes. Now, when I take a look at the forces in the x direction, equals mass times any sort of acceleration. How do I think about this now? Well, I'm going to call to the right positive, to the left negative. And do I know exactly what that friction force is? Well, I think we'll kind of have to take a look at that. I can find probably the acceleration in the x direction here if I really kind of want to. Now, I've got 20 newtons here. I'm going to drop the units here just to keep this cleaner. And my friction force is a coefficient times a normal force. And I've got 5 kilograms here times this acceleration. So I'm really doing something here that looks like a chapter 4 or chapter 5 type thing. But I'm going to try to connect this up with what we're doing here in chapter 7 here, because physics is physics, right? And it should always give us the same answer here. So let's just kind of look at these mathematical details here. Someone said the coefficient here is 0.3. And the normal force is the object's weight, mass times gravity. And over here, I've got 5 times A. So I'll drop the units just to keep this cleaner. And we know what the object's mass is. It's 5. So I've got 20 here, minus 0.30. And this is 5 kilograms. And I think I'm just going to use 10 for gravity. Equals 5 times A. Okay. So what I have here is 5 times 10, that's 50 times 0.3. So 50 times 0.3 is 15. So this is 5 equals 5 times A. So maybe I get something like 1 meter per second is the object's acceleration. And, it really looks like maybe about 2 sig figs is the best I can do. So maybe I should write this as like really 1.0 or something like that. Okay, now if you want to know how fast the object is going, now you need a kinematic, right? Now you're going to need a kinematic. Its acceleration, and then we can figure out how fast it happens to be going, because someone wants to know exactly what the final speed happens to be. We don't really have a lot of information about how long it's being pulled or anything like that here at all. The kinematic that kind of comes to mind here then is maybe the third one. Okay, and so it starts from rest. So that's going to be a 0. Acceleration is 1 meter per second. I'm sorry, this pen is running out of battery, I think. And I'm going to let it move for the same 2 meters that it did before. Okay, so my final velocity squared is 2 times 1, which is 2. 2 times 2 is 4. and that's meters squared seconds squared. So my final velocity here is 2 meters per second. Okay. Good time for us to take a look at what happened to exactly the same object up here that did not have any friction. It was moving at 4 meters per second. So friction ripped us off, right? And only let speed get up to about 2 here. Okay, now notice here, I did this problem exactly like you would in like chapter 4 and chapter 5. Now, how about using this other approach, right? Maybe I'll call that method 2. The new stuff, that the work is equal to the net force times displacement, and that's what changes the kinetic energy of this object. Now, take a look, see here. We're pulling with 20 newtons, and friction here happened to be 15 newtons. Okay, so if I actually go all the way back and read this very carefully, what it says here, the net work done on an object is equal to the change in the object's kinetic energy. And there's a word in here that you have to start getting used to. That's this idea of net. Right now, if somebody pulls with 20 newtons that way, and somebody pulls with 5 newtons that way, the net is 15 that way. That's what net means. It's kind of what's left over here, right? The net work done. Okay, so if I come down here to this problem and I look at this in terms of just not forces and accelerations and kinematics, right? There's a lot of stuff there. There's a free body diagram. I looked at the forces in the x direction. I looked at it in the y direction. I needed a kinematic to get an answer. I could use this idea of net work equals the change in kinetic energy. Now, net work means I need the net force, right? So this is the net force times the displacement equals the change of kinetic energy. We'll have it starting from rest. So that goes out. My net force here is 5 newtons. I'm pulling with 20, but friction is pulling with 15. So this is 5 newtons. And I'm going to pull the object 2 meters. And I've got this 1/2. The object's mass is still 5 kilograms. And here's my final velocity. Okay. So it looks like I've got a 5 on each side. So I just cancel those out. 2 times, I'll get that 1/2 multiply. So 2 times 2 is 4 equals my final velocity squared. And means that my final velocity here is 2 meters per second. Okay, so we get exactly the same answer, right? It doesn't matter if we use chapter 4, chapter 5 methods, or we use this new method. The object needs to be doing what the object is doing. And what we need are mathematical techniques that can give us that answer, as well as a conceptual understanding here. But it's this right here, the net work equals the object's change of kinetic energy. So if I've got more than one force acting on the object, I need to find the net force. The net force, add them up. 20, 15, the net force is 5. Okay, so these are the ideas that are going to be really put into play in something like chapter 8. Now we're going to start looking at fundamental laws of nature, and that will be the conservation of energy, also called the first law of thermodynamics. That in a closed system, the energy content will be conserved. The energy can change forms, but the overall energy content will always be conserved. And since we're introducing the first law of thermodynamics, I'll also probably introduce the second law of thermodynamics, which for those of you that go into Physics 102, that will be a very prominent chapter in the learning there in something like that. So this will kind of wrap up, the main ideas showing up in chapter 7. So there are some new definitions here. The idea of work, the idea of kinetic energy, that is translational kinetic energy. Know those two definitions, right? Kinetic energy is 1/2 mv squared. Work is the integral of FD, the displacement. And then there's also this idea of the work energy theorem. Know that, or the work energy principle, and know how to work out with the IJK notation for vectors and the vector dot product, or the scalar product. So those are really the main ideas that are showing up in chapter 7. You really kind of want to have those at your fingertips so that it becomes useful tools in chapter 8. Otherwise, if you don't really kind of have a good mastery of those, then chapter 8 is very, very difficult for you because you're kind of flailing with concepts that you have not really mastered, in chapter 7. So dig your heels in and try to get this stuff to make some sense. So, work through the lecture, work through the examples that I did here. Make sure you can kind of do these. Work through the textbook. He has a lot of very good conceptual and numerical examples. And then finally, try to tackle your homework, right? Once you built that foundation, then you should be in pretty good shape to be able to handle those. And we'll then take a look at those problems that you might have in discussion. Otherwise, hopefully this goes pretty well, and I will see you soon.